Today we're going to be looking at atom economy, but to get us started I thought we'd look back at C2 and have a little think about ionic bonding. So have a go at the quick questions here. If you want to dig a bit deeper, try them now, try these. Pause the video and we'll go through the answers when you're ready. So how did you get on with these? Let's have a look through them. First question asks you, do ionic compounds have high or low melting points? Well, they have high melting points. You might have direct experience of this. Sprinkling salt on your fish and chips, you'll notice the salt doesn't melt and disappear, it stays in that crystal structure. And you may have in year 9 gone into the lab and heated some salt very highly on the Bunsen burner, 100 degrees Celsius, and not had it melt. Now, why does this happen? Why doesn't it melt? It is because of strong electrostatic force of attraction between those positive and negative ions. But also, it's not on the diagram here, they have many bonds. It's a giant lattice structure. So not only is that force of attraction really strong, there are lots of forces of attraction that need to be overcome. Question 2 asks, what's the limitation of the ball and stick model? So if you think of those models we kind of pass around the classroom, what are the limitation of those? Now, there may be lots of ideas that you have come up with that aren't on this answer sheet here. So don't worry, there are lots of answers. But 2 to be getting on with is the relative size of the ions. They tend to be shown the atoms all the same size and the ions all the same size. That's not the case. We know some atoms and ions have more shells than others, for example. We also know there aren't any gaps between the ions, and the models that we look at kind of imply there is. Question 3 is a really common exam question. So why does an ionic substance conduct electricity when molten but not when it's solid? So we need to think about what electricity is. So electricity is the flow of charge or flow of electrons. So we will have covered that in physics quite a lot. So if we want an ionic substance to be able to conduct electricity, it needs to be able to carry the charge. And when it's in its solid form, it is in a rigid lattice structure. There is no movement, no flexibility, there are no free electrons. When it is in a molten or in solution, then those ions are free to flow through the structure or flow through the solution and carry the charge with them, okay? So solid, they're in a rigid structure, there's no ability to carry the charge and move it along. When it is molten, those ions are able to move around. Question 4. So we have the diagram to look at and you're asked to describe it. So it's a giant ionic lattice structure. We've got those ions closely packed together, a regular repeating pattern, that's what a lattice is, regular repeating pattern, held together by ionic bonds, and there are strong force attractions in all directions. It's not a 2D model, it's in all directions. Last question, you were asked to look at the empirical formula of calcium chloride. So you're told that calcium is in group 2, so it forms a 2+ ion, and chlorine is in group 7, so you know that it gains an electron will have a -1 charge. So we also know for a compound to be stable, it needs to be neutral overall. So we need the net charge of calcium chloride to equal 0. That means we need to have 2 chlorines, so that gives us an empirical formula of calcium chloride, CaCl2. So, back to the main aim of today's lesson, calculating atom economy. So first job, bit of revision here from when we did C3 originally, work out the formula mass of the reactants in total. So we have the equation here, we've got methane plus water forms hydrogen gas and carbon monoxide. And we have a second question of how efficient is combustion at producing hydrogen. So, first task, reactants. That's the stuff on the left hand side of the equation, the things we're reacting together, methane and water. And we're asked to work out the formula mass. So to remind you, we're going to take the mass numbers for the carbon, the 4 hydrogens in methane, add them together, and we're going to add the mass numbers for the 2 hydrogens and the oxygen and water, and we're going to add those all up together. And that kind of tells us the mass of all the reactants we have together. So that's going to be the first part. And then the question says, how efficient is the combustion at producing hydrogen? Well, how would you have a go at that question? Have a think for yourselves, pause the video, have a go before you move on. So let's look at the first part of this question. Work out the formula mass of the reactants. So we have the formula mass of methane. So we've got the mass number of carbon is 12. We've got 4 hydrogens and the hydrogen mass number is 1. So we're going to do 12 plus 1 plus 1 plus 1 plus 1, which gives us 16. And then for the water, we're going to have 1 plus 1 plus 16, which equals 18. So the total formula mass of the reactants is going to be 16 plus 18, which is 34. So we've done the first part of this question. Now let's look at the efficiency bit. Now another way we could phrase this is how much of what is produced is hydrogen. So from the total reactants we had, how much of that makes the hydrogen that we're interested in? So we know the formula mass of the hydrogen gas, H2, is going to be 1 plus 1, so that's 2. But we've also got 3 moles of it, so it's going to be 3 times 2. So that we know that we've got an MR of 6 for the amount of hydrogen that's produced. So we know how much hydrogen is produced, we know how much we had of reactants. What is that as a percentage? How efficient is this? So if we want a percentage, we take the MR of what we're interested in, we're going to divide it by the amount of reactants we had, the MR of the reactants, and we're going to times by 100, and that gives us 17.6%. If we look at that as a formula, we've worked out atom economy. Atom economy equals the MR of the question's focus divided by the MR of the reactants, and we times that number by 100. This is a need-to-know equation, so make sure you have a copy in your notes. So why are we interested in atom economy? Well, the major point of interest is looking at minimising waste. So we're not wasting money by throwing away things at the end, or producing pollutants, or buying unnecessary amounts of reactants. So here in this question, which I'd like you to have a go at, we're looking at the different ways you can make zinc sulfate, and there are 2 methods shown. Now the question here asks you just to work out method 1, but if you'd like to dig a bit deeper, it'd be worthwhile you having a go at method 2 and doing a comparison. So as scientists, we can look at 2 different methods and we can make a judgment over which one is best based on their atom economy. Have a go at calculating for method 1, and do please have a go at method 2 and see if you can make a comparison, that little bit of digging deeper. So for method 1, you should have got 161 divided by 81 plus 98, times that by 100 to give you a percentage of 89.9%. And if you had a go at dig deeper and looked at method 2, you should have got atom economy of 72%, showing that method 1 had a greater atom economy. So we can see how chemists can calculate the efficiency of a reaction and make judgments. We can also make judgments on a reaction based on its theoretical yield. What in theory, or how much in theory, should this reaction produce? And that's what we're going to go through next. So the first step when calculating a theoretical yield is to balance the chemical equation, make sure that's all balanced. So first job, balance the equation. You then want to calculate the molar mass, and we're going to look at the reactants first. So we're using the same method for working out MR that we used earlier. So we're looking at those mass numbers on the periodic table and using those to calculate them there. So we can see oxygen's MR and glucose, that's what C6H12O6 is in that little diagram there. So the equation we're looking at relates the reactants and the products to each other through their moles, so that we can see from the equation that if we've got 6 moles of oxygen, it will react with 1 mole of glucose to form 6 moles of carbon dioxide and 6 moles of water. That comparison doesn't work with masses and grams, so we need to convert our information we're given into moles so that we can make comparisons. So if we take, for example, we've got 40 grams of oxygen at the beginning of the experiment and 25 grams of glucose, we can work out our moles of oxygen and our moles of glucose. So to work out the moles of oxygen, we're going to take mass divided by MR, so that's 40, divided by 32. That gives us 1.25 moles. Then for the glucose, we're going to take the mass of 25 grams, divide it by 180, which equals 0.139 moles. Now, looking at the equation again, we can use the molar ratio to give us a bit more information. So the molar ratio tells us the proportion in which these reactants react together and how much relative to each other they produce in products. So we can see from this equation that 6 moles of oxygen will react with 1 mole of glucose to form 6 moles of carbon dioxide and 6 moles of water. So we could double the number of moles and everything would double in the same proportions, and we could half it also. So if we had 3 moles of oxygen, it would react with half a mole of glucose and so forth. Now, the other useful thing about looking at these ratios is that we can identify something called the limiting reactant. What is going to limit how much can be produced? So we know how much we have of oxygen and glucose in this reaction, and we know how many moles we have. So we've got 1.25 moles of oxygen and we've got 0.139 moles of glucose. So do we have enough to produce the maximum number of moles of products we think we can produce? So one way we can do this is that we know that we have 6 moles of oxygen react with 1 mole of glucose. So let's take 1.25 moles of oxygen and divide by 6 to tell us how many moles we need of glucose. So if we do 1.25 divided by 6, this gives us a mole number of 0.21. That is more than the number of moles of glucose that we have, which is 0.139. So this tells us that glucose is a limiting reactant. So we're going to do the next part of the calculation using the moles of glucose, because that's our limited reactant. Once that's all used up, we're not going to produce any more product, even if we've got an excess of oxygen there. So we know if we've got 1 mole of glucose, we're going to produce 6 moles of carbon dioxide. So looking at those ratios, we're going to want to times that 0.139 by 6, and that will give us 0.834 moles of carbon dioxide. So using the formula mass and multiplying by moles, we're rearranging that triangle. We can say, theoretically, the mass of carbon dioxide produced is going to be 0.834 times 44, which is the MR of CO2, and we should produce 36.7 grams of carbon dioxide.